This is the Module 1 End of Module Test Review Tour Part 2, questions 8 through 15. So we're halfway there, no point in turning back now. Bruce has a hardwood floor business. He gets the job to put wood floors in Store 1 in the mall. Bruce reads the blueprint of the mall to plan the job. 3 inches of length on the blueprint corresponds to an actual length of 42 feet. So, number 8, what is the scale factor? So, our goal, this is our goal. Express the scale factor as a comparison of inches on blueprint to actual number of inches in real life. So here is the map of equivalent ratios leading us toward our scale factor in inches to inches. Go ahead and work to fill in the numerators. So here we divide each quantity by 3 for 14 feet to 1 inch. We multiply 14 feet by 12, we have 168 inches to 1 inch, and we express that in this notation, 1 inch to 168 inches. Number 9, if the dimensions of Store 1 on the blueprint are 6 inches by 8 inches, what are the actual dimensions in feet? So we have a store in the shape of a rectangle on paper. It measures 6 inches by 8 inches. And we need to apply a scale factor, figure out how many feet would this much larger rectangle measure. And so a useful ratio, if we bring with us this ratio that 1 inch in the blueprint corresponds to 168 inches of actual length. Whoops, I meant to circle this one. If we say that 1 inch on the blueprint corresponds to 14 feet of actual length, that can be a helpful ratio for us to determine the dimensions of the store. So to find the actual dimensions, I'm going to multiply each dimension on the blueprint by 14, or 14 feet. So that, when I multiply 6 times 14, gives me 84 feet. 8 times 14, 112 feet. So our store dimensions, our actual dimensions are 84 feet by 112 feet. Number 10. 1 box of wood floorboards will cover 48 square feet. How many boxes of wood floorboards will Bruce need to buy to finish the project? So remember what we found in question 9. We have a rectangular store that measures 84 feet by 112 feet. And they're going to cover the space inside that store with a wood floor. So for each box, it's going to cover some fraction of the area inside the store. We need to figure out essentially how many groups of 48 square feet will cover the area inside the store. Step 1 in doing that would be to calculate the area. We need to know the total number of square feet inside the store. We can see that to calculate the area, 112 times 84 gives us 9,408 square feet. Now they're going to start covering that space with wood floorboards. So 1 box would cover a fraction. And then they're going to need another box. And so we're sharing this space or this area with groups of 48 square feet. So how can we figure out how many boxes they will need to finish the job? So step 2 would be to divide 9,408 square feet by 48 square feet. And when we do that, we would get 198 boxes required to finish the project. So at this point, we still have our character Bruce in his wood floor business, but this question is not related to the previous questions about the actual dimension. So while it's the same character, this really begins a new question series, something separate from number 10. We wouldn't want to be looking for information from numbers 8, 9, or 10 to answer question 11. After the first 20 minutes of laying down wood floorboards, Bruce has used 1/4 box of wood floorboards. What is the rate that Bruce is laying down floorboards per hour? So one thing that would be helpful to do would be collect some data in our table X, Y. But we need to identify what is the X variable and what is the Y variable. So first of all, what will be X? Minutes or boxes? So maybe a better way to phrase that question would have been time, really. What would be X, time or floorboards? And we can see that X is going to be time. And so that makes Y the number of boxes. So we see data organized in the table X, Y, 20 minutes, 1/4 boxes. So the question is asking us, well, what if we put 1 hour here, what will be the number of boxes? That's not meant to be a 7, that's meant to be a question mark. When we compare data, Y divided by X, we would have 1/4 boxes per 20 minutes. And our goal, we could do this with equivalent ratios. Our goal would be to say, well, how many boxes would that be out of 1 hour, which is 60 minutes. So how could we find the number of boxes they would put down in 1 hour? So 20 minutes times 3 equals 60 minutes. So if we multiply our numerator by 3, we find the equivalent rate, 3/4 boxes per 1 hour. So there's our answer. We could express this as a rate, 3/4 boxes per 1 hour. Number 12, write an equation that represents the relationship between the number of boxes Y in X hours. So 11 and 12 are certainly connected. In fact, we've done the work we need to do in 11 to write our equation. So think about what number in 11 we've already found that we'll use in our equation, and go ahead and write it. So remember, to write our equation, we need to find the constant of proportionality k. And what value of x, if y is k, what value of x allows us to identify k? That value is x equal to 1. So in our table of x is 1, y is k. In a rate, in the denominator, x is 1, y is k. And so we see x equal to 1, or 1 hour in the denominator, so k equals 3/4 boxes. So we have our equation of the form y equals kx, and we'll reserve a spot for k. So we will substitute 3/4 for k, and here we have it. Our equation is y equals 3/4 x, or the number of boxes is equal to 3/4 times the number of hours, x. So here is another point in where we change to a new group of problems. We still have Bruce, but again, we want to treat 13, 14, and 15 as its a new set of problems. And we don't really need to be bringing things with us from question 12. Question 13. Bruce hires a worker named John to help him finish putting the wood floor in store 1. Bruce works faster than John. Bruce puts down 3 boards for every 1 board John puts down. Is the relationship proportional? Explain your reasoning using a graph on the coordinate plane. So here we can see Bruce and John are already assigned to the axes of the graph. So that makes Bruce x and John y. And so one step would be to collect some data in a table. We would need at least 2 coordinate pairs x, y to test the relationship in a graph. So what we see is for every 3 for Bruce, 1 for John. And that would continue. When Bruce puts down 6, John has put down 2. So this could continue. Could say 9, and then for Bruce, and then John would be 3. So now we have some data that we can graph on the coordinate plane and test it to look for a proportional relationship. So here is the data: Bruce 3, John 1. Bruce 6, John 2. Bruce 9, John 3. So step 2. So now the next step would be to put a straight edge to the points and then extend that line in both directions. Kind of hard to do without a straight edge. But what we'd see is if we line up our straight edge to the points and extend it in both directions to the edge of our graph, what does our graph tell us? The graph is telling us yes. The graph, it is proportional. Yes, the graph is a straight line intersecting the origin. 14. What does the point 0, 0 represent in terms of the situation being described by the graph you created in 13? So remember that this point, any dot on a graph, is a complete sentence written in algebra describing Bruce laying down floorboards and John laying down floorboard. So an example of what that sentence could be is that when Bruce has put down 0 floorboards, John has put down 0 floorboards. It needs to be a complete statement including both the x and y variables and the quantities 0 and 0 from the coordinate pair. 15, the finish line, the final question. Which point on the graph represents the number of boards Bruce puts down if John puts down 6 boards? So we want to think back to 13 and how we identified Bruce as X and John as Y. And we can actually bring the table we had created in 13 bring it with us to help answer this question. So remember the table we created. And then in the problem it says if John puts down 6 boards, so where does that 6 go, in X or Y? So 6 goes in Y, and so we need to imagine this pattern continuing until Y equals 6. We could do that with our table. It says we left off with John equal to 3. If we keep going, 4, 5, 6, we need to find out how many Bruce would have. We could also think about this equivalent ratio. 3 to 1 is equal to what out of 6? So when we continue our table, we get to Bruce would be at 18. Or we could say, well, 1 times 6, we could say 1 times 6 is 6, so 3 times 6 would be 18. So the point would be 18/6 to figure out how many boards Bruce had laid at the point when John had put down 6.